Well, this evening, we're privileged to have Dr. Jerry Dunifer, I was going to say speaking to us, but he's going to be doing more than speaking to us. It's going to involve a demonstration of the physics behind some of the basic stuff going on out there, including a demonstration of conservation of angular momentum and some demos of how cold it can be in some places. Jerry is Professor Emeritus in the Physics and Astronomy Department at Wayne State University. He enjoys observing solar eclipses, visiting astronomical observatories around the world, and I think he gave a presentation to us about some of that, I don't know, a couple years ago, or I don't remember how long. Last year?
18 months.
18 months ago. He also enjoys sailing, flying airplanes, and traveling to exotic locations such as the North and South Poles. He must have brought some cold back with him. So, Jerry, you're on.
Okay, thank you, Dale. Can you hear me in the back?
Yep.
Okay, well, this presentation is going to be a little bit different than what is normally given, because I'm going to go through a number of demonstrations. These are demonstrations that we use down at Wayne State University, both in the classroom and for outreach activities. Some of you have probably seen these before, because we have used them at various astronomy events around the area, such as out at Kensington Metro Park or Lake St. Clair Metro Park. But I'm guessing probably a number of you have not seen them, so I thought it'd be worthwhile to bring them in this evening and show them to all of you. I'm going to be illustrating two different topics. One is conservation of angular momentum, and the other one is taking a look at the cold temperatures that are experienced in the outer regions of our solar system. So if we look around the universe, we find that there are many objects out there which have rotational motion, rotating on their own axes or in some type of an orbit about the center. We have our sun, which rotates approximately once a month on its axis. We have the planets, which travel in orbits around the sun with various periods. We have spiral galaxies like our Milky Way galaxy, which rotate. And as a consequence of that rotation, our own sun goes around the center of the Milky Way approximately 4 times every billion years. One of the main things from physics that determines the nature of this rotation is a very important law which comes out of physics known as conservation of angular momentum. This comes directly from Isaac Newton's equations of motion and plays an important role in determining just how fast things rotate that we find throughout the universe. Now, generally, you can think of angular momentum as a measurement of the rotation of an object, but weighted according to the mass distribution. And if you have a very simple system, like a single object traveling around in a circle, and let me get my first demonstration out.
He's going to need the lights dim for this. Do you know how to do it? Yeah.
So I have an object I'm going to be swinging around in a circle. The angular momentum in this case is there's a very simple equation, simply given by the mass of the object, multiplied by its speed, and multiplied by the radius of the circle in which it is going around. Now, this principle of conservation of angular momentum says that in the absence of an applied torque, an object or a collection of objects keep their angular momentum constant. And this quantity torque you can think of as a force applied in such a way that it would cause a stationary object to start rotating. So let me see if I can illustrate this as well. I'm going to start this object spinning again, and then I'm going to be pulling down on the string, which keeps it moving in a circular orbit, reducing the radius of the orbit. And the force I'm applying, in fact, is the force that does not exert a torque on the spinning object. Therefore, the angular momentum of the system should stay constant. So, since I'm reducing the radius, in order for the angular momentum to stay constant, the velocity should be increasing. So you should see this object going faster and faster as it goes around in a smaller circle. Okay, was that visible to everybody? Mm-hmm. Okay, conservation of angular momentum. Now, this plays an important role in astronomy because most of the objects that we find out in the universe, like stars and planets and galaxies and so forth, formed originally from gravitational contraction of much larger entities, such as large clouds of gas or large clouds of gas and dust. And as gravity pulls these objects smaller and smaller in size, this principle of conservation of angular momentum simply says that they have to be rotating faster and faster, as I've just illustrated. So I've got a few more demonstrations of this principle, and I've got a stool up here which spins more or less without too much friction. And if we can get a volunteer to sit on this spinning stool, we'll give you one more demonstration of this. Any volunteers? Any break?
I almost pulled a Simon and went, me!
We were hoping
Seriously?
I get on here, I got vertigo.
Sit or stand?
What would be more dramatic, standing? But you better sit. You better sit.
He is a unicyclist, so.
Stand on this
So
one
let's
foot.
do that exactly.
What's that?
And let me give you two weights.
Okay.
And let's turn you around to face the audience. Okay, what I'm going to ask you to do is I'm going to ask you to hold these weights out in a minute. And then we're going to start you spinning reasonably slowly. And then I just want you to pull the weights in closer to your body as you're spinning. And again, conservation of angular momentum. As the weights are moving in, you should be spinning faster and faster.
Oh boy.
So you don't get
Starting to regret coming up here.
You don't get dizzy too easily.
Yeah, we'll see.
Okay. So you can hold the weights out.
Okay.
Bring them in. Okay. And now pull them in.
Ooh, that's cool.
And then out again. And then in once more.
Wow. That's a very weird feeling.
Okay. Very good. So we'll take those back and thank you very much.
Thank you. Okay, one more example. I've got a bicycle wheel here, which I can spin. I'm going to start it spinning, and then I'm going to sit down on the stool. So initially I'm at rest, but when I turn the wheel over, I start spinning. And the reason is the system of me, the stool, and this wheel is sort of an isolated system. There are no external torques, and therefore the total angular momentum stays constant. So as I reverse the direction of spin of the wheel by turning it over, in order to maintain the original angular momentum, I have to start spinning on the stool in the same direction that the wheel was spinning originally.
Stop yourself.
Yes.
So if you reverse it back, will you stop?
If I reverse it back, yes, I should stop. Except there's a little friction in the wheel, a little friction in the stool, and I might not stop exactly, but approximately I would. Okay, now I can do one more interesting demonstration with this bicycle wheel. I could use one more volunteer. This is a much safer demonstration. Who would like to?
Dr. Parton. Oh, Ken Burton.
Go ahead,
I
Ken.
don't care.
Okay, let's see. Let me try and move it back just a little.
Your name safe off.
Okay, now I'd like you to hold one side of the wheel. I'm going to hold the other side. Now, all you have to do is, when I tell you, is let go of your half of the wheel. Okay? Now. Okay, very well done. Let's do that once more. Okay, so when I say go, just doesn't release it. Everybody watching? Okay, go. Okay, so as you would expect, the wheel simply flops over and falls down. I want to do that again, but this time with the wheel spinning. Okay, I'll get the wheel spinning real fast. Okay, and let go now. Okay, so the outcome is rather different in this case. And since that's so cool, we'll do it one more time. All right. Let me get it going again. Okay, you can take that. And release. Okay, thank you, Ken. Now, what I just illustrated is something called precession. And in this case, there is a torque which is acting on the wheel. That's due to gravity pulling the wheel down, so when Ken lets go, it simply flops over like that. When the wheel is spinning, it has a fair amount of angular momentum, and then the application of the torque, once half is released, causes a motion called precession. And that's where you see the axis staying approximately horizontal and the wheel going around like this, with the axis slowly spinning around in space in that fashion. Now, there's a good example of that happening in astronomy. Can anybody tell me, where is precession taking place?
Here.
Earth. Earth. Okay, very good. Yeah, the axis of the Earth is slowly precessing. The axis right now is pointing at the North Star Polaris approximately. And as time goes on, through my arm is that axis. It sweeps out a cone in space and goes round and round like this. That is precession. That is due to a torque acting on the spinning Earth. Now, the period to go completely around is about 26,000 years. So at the moment, our axis is pointing towards Polaris, but in another 12,000 years, it will have precessed considerably, and it will be about 5 degrees off of the star Vega, Alpha Lyrae. So, who can tell me where does the torque come from that causes the Earth to precess?
The sun and the moon.
The sun and the moon. Okay, very good. Yeah, the Earth is rotating, and therefore it's not exactly spherical. It's flattened at the poles. It bulges at the equator. So it is somewhat pumpkin-shaped. Because of that, the sun and the moon, pulling on the bulges, the equatorial bulges, produce a torque trying to change the rotation axis. And it's the response to that torque which gives rise to this precessional motion. Okay, I've got yet one more demonstration of conservation of angular momentum. And this is the most dangerous one for the night. What I'm going to do is I'm going to generate something called a fire tornado. following. I'm going to generate a small tornado composed of fire. This doesn't always work, but it usually does. We can leave the lights up for just another minute or so. Yeah, well, once we get it going, then we'll turn the lights down. So I've got an enclosure here, which is two pieces of plastic, with a gap between them, which is about ½ an inch wide. And so I'm going to put this right down on the stage. I'm going to start a small fire here in the center of the enclosure. And then I'm going to put a lid on top of the enclosure. So this is our lid, which has a hole in the center. Just like that. So as the fire is burning, it's going to generate a lot of hot air. Hot air rises, so it's going to come up to that central hole. And to help the process along, we'll put a chimney on top, just like that. Now, as the hot air rises, in order to keep the fire burning, we have to get fresh air entering this enclosure. And that is where these slits on the side allow air to come in. So this ½ inch gap over here and the ½ inch gap over here allow air to come in such a way that that air is slowly going round and round the inside of the enclosure. But as hot air escapes up the chimney, that circulating air is brought in closer and closer to the fire. And conservation of angular momentum means that that air has to spin faster and faster. So it starts out fairly slow at the walls of this enclosure, but as it gets in close to the fire, it's going pretty fast. And if all works well, it will be going fast enough that it's going to whip this fire into a little tornado, or a mini tornado, or our fire tornado. So we'll give it a try and see if it works. What's that?
Check your liability insurance.
Absolutely.
I'll sell it.
Okay, so we're going to start with a little tornado fuel. This is a secret formula which is not exactly rubbing alcohol. It's 200 proof.
Drink it first.
Well, one could. Okay. Okay, is everybody ready?
Yeah,
Here we go. Okay, so the fire is going. And we'll put the lid on. And the chimney. Okay, so now we've got a lot of hot air coming up the chimney. So as the cooler air is pulled in the sides and begins to swirl around, coming in closer and closer to the fire, you can see the fire now starting to go around in a circular pattern.
Very cool.
Okay, so the air is getting in closer and closer, faster and faster.
Oh.
Here we go.
That is very good.
So just how long have you been worshiping Satan?
Some years. Okay, we can't let it go very long, otherwise it starts to melt the plastic. And there you are.
Wayne State University gift shop?
No, I do not. We had to make it ourselves. And I have not seen these available anywhere for sale. But if you like, you can come up and take measurements and make your own. It's a fairly easy construction. Now, one last example of where this happens in astronomy, in fact, a rather extreme example, is the creation of pulsars or neutron stars. These are little tiny stars about 10 miles in diameter, made mostly of neutrons, and they spin very fast on their axes, typically several times per second. The way they come about, well, let me say the most famous one is the Crab pulsar, which is in the center of the Crab Nebula, which is a result of a supernova explosion, which was seen back in the year 1054 AD by the Chinese and recorded in great detail by the Chinese. What they observed was a very sudden bright light which appeared in the sky, which was visible even during the day and remained visible for quite a few weeks and gradually faded out. So this was a supernova explosion, a type 2 supernova explosion, which results from the gravitational collapse of the core of a massive star. So at the end of the life of such a star, what happens is there is insufficient pressure generated in the core to support the core, and the core undergoes gravitational collapse. Electrons and protons are pushed together, combining to form neutrons, and you end up with an object which is mostly neutrons, and they occupy a very much smaller volume. So in this process, the original core, which might be 10,000 miles in diameter, undergoes a sudden collapse within about a second or so, down to this neutron star, which is about 10 miles in diameter. Conservation of angular momentum says that whatever the original spin rate was of the core, it's going to be increased considerably by this sudden collapse. So if the diameter goes down by a factor of 1,000, the spin rate goes down by a factor of 1,000 squared or 1,000,000. So the object after the collapse is spinning 1,000,000 times faster than it was before the collapse. So with the Crab pulsar, when we look up in the center of the Crab Nebula, we find this little neutron star spinning on its axis 30 times a second. And that very rapid rotation is due to this principle of conservation of angular momentum. So we know nowadays that for each rotation we get a flash of electromagnetic waves like light and radio waves. And so if we look today up at this object, we're seeing 30 flashes per second due to the rotation, even though it's been almost 1,000 years now since the supernova explosion took place. Okay, so that's the first thing I would like to be demonstrating. The second topic I want to go through fairly quickly has to do with the types of temperatures we find in the outer solar system. So as everybody knows, the inner planets are hot, the outer planets are cold. Planet Mercury reaches a temperature about 800 degrees Fahrenheit on the day side of the planet. And of course, when you go out far into the solar system, the temperature is much lower. So how low can it get? Well, the intensity of sunlight is inversely proportional to the square of the distance from the sun. So the most distant planet nowadays is Neptune, and that's 30 times further from the sun than the Earth is. So that means that the intensity of sunlight out there is 30 squared, or 900 times less than it is at the Earth. So the sunlight is very feeble out at Neptune, and the temperatures are very cold. Well, back in 1989, Voyager 2 passed through the Neptune system, sent back extensive data on the planet Neptune, and also its largest moon, Triton. And what it reported back was that the temperatures on Triton were at approximately 393 degrees below 0 Fahrenheit. So that is so cold that it probably makes more sense to describe how far above absolute 0 that temperature is, or the temperature in Kelvin.
So in terms of Kelvin, the temperature measured on Triton was 37 Kelvin,
Oh, wow.
minus 393 Fahrenheit. Now that temperature is so cold that almost nobody on Earth has had any experience interacting with the temperature in that range. In fact, speaking of the Earth, who knows what the coldest temperature is that's ever been recorded on Earth?
150?
Minus 150?
Yeah.
In that ballpark, yes.
120.
Minus 120. In that ballpark. Yeah, there was a report that came out last year, satellite data, looking in the infrared. They measured what appears to be a temperature of minus 136 degrees Fahrenheit. This was on a range between a couple mountains at about 13,000 feet above sea level during the dark of the winter, minus 136 Fahrenheit. So that's the coldest that's ever been measured on Earth. Going out to the moon Triton, the temperatures are so cold that normal gases that we are acquainted with down here on Earth, like oxygen, nitrogen, methane, ammonia, they are all frozen solid on the surface of this moon. Surprising, however, when Voyager 2 went past, it actually recorded some geysers, or volcanoes, which were erupting on the moon. These appeared to be geysers, or volcanoes, composed of liquid nitrogen and gaseous nitrogen, which were emitted from the surface and going up about 5 miles above the surface. How did this happen? Well, it's thought that probably the sunlight shining down on the solid nitrogen surface, solid nitrogen is transparent like glass, was able to go some distance below the surface and warm up nitrogen below and form pools of liquid nitrogen. And it was these pools of liquid nitrogen which broke through the surface and produced these geysers. So I'm going to illustrate these type of temperatures to you now. I don't have anything quite as cold, but I have brought in liquid nitrogen, which is a little bit warm, but it's in the same temperature range. So liquid nitrogen is 321 degrees below 0 Fahrenheit, or 77 kelvins. So let's take a look at that. I'm going to pull this table up a little bit. Okay, I've got a container which is called a dewar. D-E-W-A-R, which is like a giant thermos bottle. It was very good at keeping hot things hot or cold things cold. So we've got a few liters of liquid nitrogen in here. I'm going to pour it out into the beaker, and hopefully you'll be able to see it. Looks pretty much like water.
You're seeing tiny ice crystals from humidity in the air freezing.
That is correct. It looks like water is boiling furiously because the beaker I poured it into is very hot compared to the normal temperature of the liquid nitrogen, 77 Kelvin. But boiling is a cooling process, so this is cooling the beaker down, and in a few more seconds the boiling is going to slow down a lot. And we're going to have our liquid in here. The vapor that you see, in fact, is tiny ice crystals which are formed in the air because of the cold. If we were to do this in a nitrogen atmosphere, and I've done this before, you see none of this cloud or vapor. It's totally the gas is totally invisible. But the water vapor allows us to see what looks like clouds being formed.
Okay, so the boiling has pretty much slowed down. It's still boiling because it's still in a very hot environment. It's very much like a pan of water on a hot stove, which is boiling slowly. You get down to these temperatures, the properties of materials change considerably. So I've got some rubber tubing here, latex rubber tubing, which is soft and flexible. And what I will do is I will put it into the liquid nitrogen. And the liquid begins to boil again faster until it cools down the rubber tubing. We'll let it sit there for a few seconds. Then I pull it out and we'll examine the properties. And what you'll see is it's no longer soft and flexible. It's rather different. It looks like it's pretty well cooled down. Let me pull it out now. I'm going to try to straighten it. It doesn't work. It's hard as a rock. It's as brittle as glass, and if I were to hit it with a hammer, it would shatter like glass. It would be little pieces of frozen rubber which would be flying around the room.
And it goes back to room temperature, back to saying it was original.
When this goes back to room temperature, it will be the same as it was before I cooled it down. Now, if you want to see a liquid nitrogen geyser or volcano, I stick one end in here. What we usually get, you see the liquid coming out? There you are.
That's easy.
So there is our liquid nitrogen geyser or volcano.
And that's what's happening on the surface of Triton.
That is what's happening on the surface of Triton in regions where the sun is shining on solid surfaces of nitrogen, warming up the nitrogen below the surface, forming pools of liquid which then force their way through the surface.
And there's enough, that's just enough heat for that to happen there. And
That's
there,
right.
of course, there's heat all around, driving up the liquid up through the rubber tube.
That's right. Now, everything is hot when I put the rubber tubing in. Because of the rapid boiling taking place, some of the boiling liquid is forced up through the tube. Okay, let me try a balloon. Getting it just so barely fits inside the beaker. You can cool the balloon down to 77 kelvins. Okay, in we go. And what do you think will happen?
Shrink.
Yeah, it's going to contract. The air inside the balloon is going to get cooled down, it's going to contract, and the balloon is going to shrivel up. It will actually come out looking pretty much like a pancake. So that takes just a few seconds to cool down completely. I am keeping my fingers on the liquid.
It's not a bad idea, too. I mean, that's got to be cold when it was a couple of days.
That bird gets really nice, wasn't it?
Well, it doesn't burn, it freezes. So, when about at the age of 21, in the research lab, we started using cryogenic liquids like liquid nitrogen, liquid hydrogen, liquid helium, and so forth. So I've worked with this for about 50 years. So I think I know what I'm doing. One's got to be careful. So if I take the balloon out now, it's as flat as a pancake. Instead of there, it'll warm up pretty quickly because it's now exposed to the room temperature around it. And as it does, the air inside is going to expand, and it's going to blow the balloon up again from the inside. It doesn't take too long. Actually, what happened, the temperature was so cold that the air inside the balloon liquefied. We had liquid air inside the balloon. So that very quickly, once I take it out, evaporates, and the gases there blows the balloon up, and very quickly it's back to the original size and shape that it was. It's pretty much unaffected. So my time is up in 1 minute. So We'll do it once more with the balloon. When I do this for elementary school kids, they always want me to put my fingers in the liquid and freeze them.
You first.
Yeah, you first.
Yeah, right. I've not done that. And what we do for them, instead of using fingers, we usually take roses and freeze the roses. So I brought in a few roses. And once it's down to 77 Kelvin, the petals become very brittle, and just a little bit of pressure, they just shatter like glass into hundreds of pieces. So we'll do that for you. We'll kill a rose. There's going to be a few roses left over, so anybody who wants to take a rose with them, or her, we're going to have 1, 2, 3, 4, 5, 6, 7. We have 7 roses after the demonstration. Feel free to come up and get one. You can actually put your finger into the liquid for about a second. Your finger is so warm it forms a gaseous pocket, and so you don't actually make contact with the liquid. There's just very cold nitrogen gas around your finger. And you can leave your finger in for about a second, but then it cools down very fast and you feel a strong inclination to take it out quickly. So that's about it. Okay, so I guess we'll go with this rose. It's going to take a few seconds to cool down. If there's any time afterwards, I'd be happy to do the fire tornado once more, and you can come up close and then give a good close view, if there is time. And let me also mention that Dale Parton wouldn't know the schedule, but Ed Catkin from our Department of Wayne is coming and talking about neutron stars and pulsars. Is it about June?
I can tell you in a moment. He's coming in May the 4th.
Oh, May 4th. Okay, that is his main research area, studying compact objects like black holes and neutron stars. If you want to learn more about them, these amazing objects, 10 miles in diameter with horrendous densities, May 4 will be a good time to come in here and talk. Okay, the rose is cold. You can pull it out. We are rose at 77 Kelvin. And we just little petals a little bit. Very brittle, just like thin glass. Okay, that's the end of my talk. Thank you very much. Well, the nitrogen will continue evaporating. If there's any left, and there's more in the dewar, after everything's over, you can come up and put your fingers in the liquid nitrogen. Just for a second, of course.
Thanks for the offer.
You just dumped it out on the floor right now. Very little we're making for the floor with it.
You want me to do it?
Sure.
Wait, can we put our fingers in it first?
I don't want to be here when you do that.
Okay, at the end, the adventuresome ones can come and put their fingers in the liquid, then we'll pour it out on the floor.
I hate to hear the truth. I am going to do this weekend. I am.
How long are your fingernails can you do that?
Normal life.
I would think you want to
Be careful.
It's up there.
Well, Jerry, I think that was really neat. Felt like a kid again. I remember working with liquid helium when I was a grad student and having various mishaps.